Okay. And for a special case of, for example, this case, we had an analytical solution known to us. Okay. What we want, so these are the two test cases that I have specified, and the method that we are going to use, okay, will be applied to these two test case problems, okay, and you can check the answer, okay. Actually, these are actually, yeah. So here gx has a form of square wave. One case, other case gx has a form of this, okay. These are the two test cases we are going to check, okay. But let me just tell you the procedure for a general case, okay. So for general case, let's see. So generally, applying finite difference scheme. Okay. All right. So general case, I can write it again. We will be having in rectangular domain. Okay. So let's say I am looking at a rectangular domain of x and y ranging from let's say x equal to 0 to x equal to a, y equal to 0, y equal to b, and we are going to divide this in. So if you recall, our scheme was equation is of course del square u by del x square plus del square u by del y square equal to 0. This is what happens over this domain, okay, this entire domain. And additionally, there are conditions specified. So conditions here we are going to keep general. So conditions would be the u as a function of x and u as a function of y on the boundary. Right? Four boundaries: this boundary, this boundary, this boundary, this boundary. Okay. So on these boundaries, I'm going to specify. Question. Oh, I see. So 3D plot. There is a command for that. How to do 3D plots? Okay, you are in. So I think. Well, I can't recall. But if you just type in 3D plot help 3D plot. I guess plot 3. I think it's plot 3D or something. The command looks like plot 3D or something. So look at the syntax of, suppose we have a data x, y, z kind of data. Okay, x, I, y, I, z, I suppose it's probably plot 3D, the arrays x, y, and z. I think this is how it's done. Okay, but please check. Because I don't tend to remember these commands. Okay, if there's a need, you can always get the help. Okay, so please check that. It's fairly easy. You can even find it on. You just go to MATLAB website. You can help find the help. Right. That's good thing about such softwares. You can always quickly find out what is the syntax. You don't need to remember. Okay, unless you have a reference manual available with you, that will be useful. Okay. All right. So is that all right, Satvir? Okay. All right. So yeah, there's a definite format of the data. There are some constraints. For example, remember for each x must correspond to y and z. So there should be n data points. Then it has to be, each should be consistent. Like it's not like x1 and y1 and z1 should appear in a single row. x2, y2, and z2 should appear in a single row. So okay, so you can just check that. All right. So now xi. Okay. So boundaries are, these are my boundaries, right? These are my boundaries. So let me call. So u as a function of y would be specified on left boundary. Let's say u as a function of y is specified on left boundary, u as a function of y specified on right boundary, u as a function of x specified on top boundary, u as a function of x specified on the bottom boundary. Okay? So I'm going to call those prescribed functions. Okay, the the functions which are applicable on the boundaries as u equal to g. B stands for bottom. Okay, u equal to gt for top, u equal to gr as a function of y, and u is equal to gr as a function of gl, sorry, gl as a function of y. Okay, so these are the functions given. So you can, so basically, if you write it mathematically, what it means to say is that u equals to gtx when y equals to b, u equal to gbx when y equal to 0. Okay, u equal to gly when x equal to 0, and gry when x equal to 2. Okay. So this is the four boundaries on the functions I've specified to you. Okay. So for example, in a previous problem, I know the problem, the test case problem, I know that this is 0, this is 0, this is 0, and this has certain form for which we have to test. Okay, so whatever method that we are going to discuss next. So, okay, so basically I've given you the example, I've given you the problem before, and we're discussing the solution technique later. Now, xi, so what we're going to do is, again, as usual, which is any finite difference scheme, we discretize it. Let's discretize it in a grid. Okay, so this is my xy grid. Okay, and according to our notation, okay, the way the procedure was, xi is going to be equal to I times h, where I is going from 0, 1, 2, n plus 1. Okay. Therefore, there are n intermediate x points and n intermediate y points, m intermediate y points, and j would be the index reserved for y coordinate, and I would be the index reserved for x coordinate. Okay? So j would be jk. K is the step size in y direction, and h is the step size in x direction. Okay, and j is going to be equal to 0, 1, 2, let's say m plus 1. Okay, so that you know h equals to a over n plus 1, and k equals to m over n plus 1. Okay, these are automatically implied. Okay, so n and m numbers of interior nodes, right? Interior nodes along x and y directions. Okay, this is our convention we are going to follow. So it's basically a boundary value problem in 2 dimensions, right? So boundary value problem in 2 dimensions, right? So here, so it's like a boundary value problem in 2D. Okay. Now, so what we do is we discretize the equation, and we use centered difference scheme. Well, actually, we use a finite difference approximation for the second derivatives. We all remember that? Further. Yeah. Thank you. Sorry. Yeah. Thank you. Thanks. Second derivative. Okay. So, well, you can just remember del u by del x, del 2 u by del x square. So u as a function of xi or yj. Okay, now we have u or n plus 1. Right? Thank you. Thanks. Anything else? Any other mistake? Okay, is wrongly written. I think I've corrected myself. Thank you, Vidya. Thanks, Amir. Okay. And thanks, Alina. All right. Thanks. Yeah. So, any other mistake? Okay. So this I'm going to call UIJ. Okay. All right. So UIJ. Now UIJ, and remember we have to find UIJ at these points. Okay. These are the points where our interior points is where my unknowns are unknowns. Actually. The variable, the known variable has no known value, and the value is not known at the interior points. Boundary points we already know that. Okay. So uij, if you do that, then del square. So let me remind you, the square can be approximated by u I plus 1 j. This is the first index, so therefore I'm going to ui j plus ui minus 1 j divided by h square, and del square u by del x del y square is substituted by the expression del ui j plus 1 minus 2 ui j plus ui j minus 1. Let's do the substitutions divided by k square. Okay. So once you do this and then define your lambda to be equal to k by h. In this case, lambda is defined to be k by h, not k square by h like you had in the diffusion equation. Here I have lambda equal to k by h. Okay. So with that definition of lambda, you can show that the equation, if you substitute this finite difference approximation in the original equation, it turns out to be, so the finite difference equation, that would turn out to be minus lambda square. I'm just skipping the detail, okay? Which we have done sufficient number of times so that you can check it yourself. Plus 2, 1 plus lambda square minus lambda square I minus 1 j minus ui j plus 1 minus ui j minus 1 0. Okay, this would be your governing governing equation that will determine how. Sorry, this ui is missing here. So lambda is lambda square ui plus 1 j plus 2 1 plus lambda square ui j minus lambda square minus 1 j minus ui j plus 1 minus ui j. So this will be the governing equation that will decide how you will change from point to point. Right? So at each point on the grid, the u's must be related. Whatever the solution is, that solution must satisfy this equation. So now, if you look at this, so for any ij, just choose any ij. That automatically, so this will be for I equal to 1 to n, j equal to 1 to n. Okay. All right. So there will be m times n such equations, right? So there will be mn equations. The total number of equations will be n times n. For each pair of I and j, I will be having one such equation. And for each pair of I and j, for each ij pair, okay, you can see that if you have a grid, okay, and say this is I and this is j, then which points u value at 5 points are actually interrelated, right? So you can see uij. First, so what are those 5 points? Uij, that would mean this point, okay? Ui plus 1j, that would be this point. Ui minus 1j, then uij plus 1 and uij minus 1. Okay, so 5 points actually are interrelated. So u value at the 5 points, 5 grid points are interrelated. Okay. All right. So this is called 5-point scheme. Actually, this is called, it's known as 5-point scheme. Okay. All right. If you recall, one of the problems I had probably given an exam somewhere. If you recall, there was a temperature problem where I had specified that temperature at the boundaries are given. Yeah, in midsem, I suppose, right? Exactly. So temperatures at boundaries are given, and point is an average of its surrounding neighborhood points, right? So any temperature is an average. So here temperature will be average of these, this one, this one, this one, this one. So this would be like here. What we know is that there's the kind of interdependency of these 5 points is stated by the simple fact, which is any point is average of the 4 neighboring points. Okay. So this way, this way these values are interrelated. So this is an example of linear system actually. Okay, here the dependency is little different. Okay, it tells me that if you assign certain weightage to this point, let's say this weight would be, let me write the weightage in the red color. So uij value, if you multiply with 2 times 1 plus lambda square. Okay, then ui plus 1j value, I multiply with minus lambda, ui plus 1 is minus lambda square, and ui minus 1j is minus lambda square. Okay, and then uij plus 1 is minus 1, and this minus 1. Okay, if you take this value, multiply with minus 1, this with minus lambda square, this with minus 1, this with minus lambda square, this with 2 into 1 plus lambda square, and sum it up, that should give me 0. Okay, so this is the kind of constraint that must be followed by u values at these good points. Okay, and these constants are actually the multipliers are actually constants, right? So therefore it's a kind of linear system. It's basically relates these values at different points in a linear fashion, right? So this a into x plus b into y plus c into z is 0. Okay, so x, y, z are interrelated in linear fashion. Similarly, here, so these are the constants. So these values are related by in a linear fashion. Okay, this is basically a linear system. Okay, all right. Uh, now it's a linear system. All right. So therefore, I want to write down these quantities which are appearing as a matrix to me. I want to write it in form of vectors. Okay. So because we know how to deal with linear systems. Okay, this linear system may be, or for convenience should be, written as a x equal to b, right? And therefore x, which is my unknown, that is u. Okay, so u vector, u actually uij, okay, should be, if your motive is to recast this kind of interrelationships in form of a linear system, then I want to recast uij as a vector, right? Should be recast as a vector. Okay, that's what we are going to do next. Okay, so okay, so let me. So here the scheme is very simple. Scheme is very simple to do that. The scheme is that I'm going to. So remember, this u has now at the moment u is specified by two index I and j, which separately give you the x coordinate, y coordinates. Okay, we can actually say it. You can represent. You can have the same information represented in vectorial format. You can always transform a matrix to a vector, right? There are different ways you can do that. So here, what we are going to do is that I have, let's say, uh, if you have a grid that looks like this, okay, okay. So let's say this is a grid. So I have to have now I have to have the same information represented as an array. Okay. So I'll have to have only one index. So now that would be done by the index would vary like 1, 2, 3, 4, 5. Don't need to go to boundary points because that's not where my unknowns. I mean, unknowns are unknowns. Actually, they're known. So 1, 2, 3, 4, 5. Then back up here. 6, 7, 8, 9, 10, and so on. Okay. So it's going to take a path. So you're going to you're going to label your data or unknowns like this, and then back like this, and then back like this, and then back like this, and so on. Okay. So that's how you're going to actually store your U's. So so you will call it now V. Okay. So Uij will be representing some VL. Okay. Okay. So any Uij, so for example, in U representation, in the matrix representation, say this is ijth point. That, so for example, let's say U32. Okay, so U32 would be 1 1 1 2 1 3 1 4. So U32 would be 3 here and 2 here. So this point. Okay, so U32 would be equal to V 1 2 3 4 5. So you can just count it 1 2 3 4 5 6 7 8 9 10 11 12 13. Okay, so U32 would be like having V13. Okay, so that is how you rearrange your data. Okay, so that's how you rearrange. Okay, so this is so now there should be a general rule of how, if I know ij, I should be able to find vl. Okay, uij equal to, let me write opposite, v of l equal to uij. V of l is equal to uij, where the simple rule is, you can check this, l equals to j minus 1 times n plus I. Okay, it's as simple as that. So, right. So, for example, let's say V1 is U11, okay, and if I take U12, okay, U12 would be what? Right, find, so ij is 1 comma 2, so L would be equal to, let's say I have 3 by 3 case, right? So say L, M and N, M is equal to 3, N is equal to 3, okay, for example. Okay, the 3 by 3 case, then L would be for one I being, for I equal to 1 and j equal to 2, L would be what? L would be j minus 1, that is 2 minus 1, that is 1 times 3 plus 1. Okay, that is 4. Okay, so that therefore U12 is the same as V4. You can check this. 1 1. So if I have 3 by 3, so let me think of 3 by 3 matrix. Okay, so 1 2, start here. Let's have the boundary points also. So here the boundary points. Okay. Here. These points. Of course, this will be on the top. 3 by 3 case would look like this. Okay, so my one, so there's this is 1 1 1 2 1 3 2 1 2 2 2 3. Okay, so 1 2 is 1 1 1 2 1 3 1 2. Right? I equals to, sorry, so I equals to 1 would be here. So 1, so this would be, sorry, so 1 1 1 2, this is 1 2, this is 1 3. So 1 2 would be 1 2 3 4, right? So this is 4. So for I equal to 1, j equal to 2, n equal to 4, right? So this is I 1 2 3, it's j 1 2 3. Let's put it on. This is another row. Yeah, because it's still this. 1 2 3 4 5 6 7 8 9. And then 9 points. I have got 3 by 3 case. 3 by 3 case. Okay. So you can see that this is first, second, third, fourth, fifth, sixth, fourth, fifth, sixth, seventh, eighth, ninth, and accordingly your V's will be labeled. Okay. So here, for example, V1, now V2 would be equal to U21. Okay. You can see that j equal to 2, I equal to 1 over here. J equal to 2, I equal to 1. Sorry, j equal to 2, I equal to 1. So V2 is U21. I have already put the sign. V6. V6 would be here, 3 2 something. So hold on. So I equal to 1, j equal to 2, so that would be 4, L equal to 4. I equal to 1, j equal to 2, that is v equal to 2. That's correct. So this is correct. Okay. So this is fine. Let's say 2, 2, 1. So 2, I equal to 2, and j equal to 1. So this is point over here. That's fine. Okay, that's fine. So this is, let me just label it ij. So let me label the ij and the L coordinates according to the figure. I have ij, I'm going to put it in red color. Okay, this would be 1, 1. Okay, this would be 2, 1. This would be 3, 1. This would be 1, 2, 2, 2, 3, 2, 1, 3, 2, 3, 2, 3. And then I'm going to put the L's in the green color. It would be 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So those correspondence between, so this is basically L and red ones are ij. Okay. The correspondence between ij and L is given by this particular formula. Okay. And is there any, but considering how we are traversing the above matrix, why should it be V6, Amit? Because V6 would be over here. As I showed, V6 is this point, that is 3, 2. If you put L equal to I equal to 3 and J equal to 2, so we can write this down as V3 will be, V2 is V2 1 and V3, so V3 would be what? V3 should be U31, right? So U31. So check that when you put I equal to 3 and j equal to 1, I'll get L equal to 3. Okay? Because j equal to 1 will cancel the first, this part, and I equal to 3, so L will be equal to I, and j equal to 1. When j equal to 1, L is equal to I, always. So I have used U31 as U3, okay? Which is what, according to my scheme, is consistent. Okay, is that all right, Amir? Any doubt about this? It's simple rule, but it just fixes your representation in vectorial format with a particular convention, that is, you are going to move this way and then back up, this way and then back up, this way and so on. Okay, that's all. Is that all right? Amir, numbering of L is not clear. Well, L, as I said, start with the bottom 1, 1 point, that is first. This is second. So as you, is the green, is the numbering according to the green color, is it all right? Do you understand that? L is according to the green color. Okay, so let me give you an example. Let's say, maybe example would be, let's say I have a matrix which is given by 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, what I'm going to do is, I'm going to, this is a matrix A. Okay, I'm going to rewrite this as 1, 2, 3, 4, 5, 6, 7, 8, 9. That's what I'm doing. Okay, I'm going to represent the same data in a different format. That's all. Okay. The above figure, we showed it in a different manner. Above figure over here, in this figure, well, I am doing the same thing. I go this way, then I come back up, I'm going this way, come back up, going this way, come back up, going this way. Why is it different? In what way is it different? I am changing my L by changing my I. Okay. Okay. It's the same scheme I'm following. That's all. Okay. So just reformatting the data representation. That's all. So rather than writing in a matrix form, I am writing it in a vectorial form, single array form, with a particular convention, which is I travel along this direction first. When I'm exhausted, come back, next row, and so on. 2 to 6 and then to 5. 3 to no. Oh, yesterday I probably, but not today. Yesterday probably I might have mentioned it this way. Yesterday I might have been, that must be wrong. Today I just say that go this way and then back up. Back up means you go back to the first one. I've been repeatedly telling you to, as you see the direction of my arrows in this black colored thing, it goes like this and then start from here and then start from here. So you have to go back. Okay? So if that was a source of mistake, source of confusion, I apologize. Yesterday I might have probably told you this way. Well, you can also do that. No one has stopped you. Only thing is that your form of the matrix will look different. Okay, you can actually try that. Try doing that. You can see how it changes. Okay, all right. So we can try that. That you can actually play around with that. Okay, but here I'm going to assume this particular convention. Okay, is that all right? Okay, let's proceed then. So having done this now, so the question is now, so once you have defined a way, once I have defined my vector V, and I have outlined the scheme of labeling it as with reference to U, okay. So basically, my original equation that was lambda squared ui minus 1j with a minus sign plus beta uij minus lambda square ui plus 1 comma j minus ui comma j minus 1 minus ui comma j plus 1, that should be equal to 0. Now these u's will actually will be now changed to v. Okay, so these u's will change to v. Okay, and how will the new equation look like in terms of v? Okay, of course you have u0 j, that is the same as gl of j, un plus 1 comma j, that is the right hand side, the function of y, therefore a function of j, and ui comma 0 is the bottom one, is the same as gb of I, and ui comma n plus 1 is equal to g top of I. Okay? These are my boundary conditions. Okay, and so the rule, and I just repeat, rule here, VL equal to uij if L is equal to j minus 1 times n plus I. Okay, for n by n case. Okay, all right. Okay, so now, let's just try a couple of cases. I'll just show you some. There's something important that has to be observed when you want to write down this in terms of V. Okay, then equation. How will the equation look like? Let's just make a list. Let's make it a small table. Let's say I have this. Let's go I J. Okay, and I have equation U. For each pair of ij, there is an equation in U, and then I want to recast it as an equation in U. Okay, all right. So okay, so now let's consider the case of well, maybe let's say I equal to 1 1 1. Let's say I'm going to change I first, 1 3 1, then I have n of 1. This would be, okay, then I have I equals to j equals to 2 equal to 1 2 2 3 2 2, okay, and then so on. Okay, so last one would be, maybe I can call it like 1 2 10. All right, so let's write down these equations. So when I1 j is 1, it's going to look like minus lambda square u01 plus beta u11 minus lambda square u21 minus u10 minus u12, that is equal to 0. Okay, and then when you write this in terms of v's, okay, this will be equal to, now you should notice that these are the constants, these are known to me. u01 is 0j is glj, so this is known to me. u10 is known to me. Okay, so I can take these are not unknowns, right? I want to write all the unknowns on left hand side and knowns on the right hand side, so I can take these on the right hand side. Okay, after taking them on the right hand side, now I'm going to write down everything in terms of betas, in terms of v's. Okay, so that would read as beta v1 minus lambda square v2 minus v n plus 1. Okay, n plus 1. So let's see. u11 is v1, u21 is v2, u12 is vn plus 1. That's done. So 1 2 u 2 would be vn plus 1. Okay, that should be equal to lambda square gl I plus, well, I is 1, so 1, and plus gv. Okay, so u01 is u01 is gl1. So from here you can check that, and u10 is gbi. u10 is gb1. Okay. These are the functions which are known to me. These are the values known to me. Okay, this will be the equation in B. Okay, similarly you can write down other terms. So maybe new case here, u1 plus beta u21 minus gamma square u1 minus u20 minus u22 equal to 0. And this, when you write down as equations for these, is this plus beta v2 minus lambda square 3 minus v n plus 2, that would be equal to dv2. Okay, the right hand side I have one term appearing, so you can write down other terms like this. Nth one, let me write down minus lambda square, okay, u n minus 1 comma 1, right? Yeah, 1 plus beta u n1 minus lambda square u n plus 1 comma 1 minus u n0 minus u n2 equal to 0. Okay, this will show up as in case of in representation of v, that will be minus lambda square v n minus 1 plus beta v n minus v 2n, that should be equal to g bottom n plus lambda square g right 1. Okay. All right. So this is how you can actually write down all the terms. Okay. So one thing is, like for example, if I go to ij11 to 12, okay. So when you go from 1 case, so if you go here over here, so if you go from 1 to 12, j will, if j is increasing by 1, okay, L will increase by n. Okay, so all you need to do here is, wherever I have second index, you just change it to 2, and L will correspondingly change by n. Okay, this 1 will become n plus 1, this 2 will become n plus 2 over here. This, so that is, so if that is what you have to keep in mind, and you can write down all the equations. Okay, so when j changes by 1, L changes by n. That you can see from our scheme itself. Okay, if you have n by m matrix, okay, so the n entry is this way. If your j changes by 1, so if you go from, for example, from here to here, you are actually L is going to change by 3 entries here. If this way it's 3 and if this way is 3, then if you go 1 point right above yourself, you are actually advancing by n points if you have traveled linearly this way. Okay, so that is, so it depends on, if there was 4 by 4 and you go one step above, you are actually traversing L, you are changing L by 4. Okay, so that is how it should be clear from this gridding. Okay, the geometry of the grid. Okay, all right, so in this manner you can construct these equations. Okay, uh, okay, this one case, I maybe one more representative case would be, let's say 2 2 maybe. So one representative case I want to state here is, let's say 2 2 or 3 2. Let's say 3 2 or 2 2, either of them. 2 2 would look like minus lambda square u12 plus beta u22 minus lambda square u32. Okay, all I'm doing is basically, I have already this equation in place. I'm just changing the second index by 1. That's all. Okay, so minus u21 minus u23 equal to 0. Okay, and accordingly your right hand, the B form would be minus lambda square v, and here it's 1, so that will go by n plus 1. Okay, plus beta v n plus 2, because j has changed by 1. Okay, going from 2 1 to 2 2. So I'm just looking at this row. It's 2 1 and 2 2. J has just changed by 1. I has remained constant. That means you're going one point above yourself. Okay, and that way your L index, which is L index, these are the L indexes. Okay? They will change by n. Okay, so that would be minus lambda square v n plus 3. Okay, minus, now here I have something, so minus v2, and we're having v2, so v2 minus v2n plus 2. That would have to be 0. Okay, so you should note here that none of these on the left hand side are known to me. So right hand side is 0. Unlike these entries where I did have right hand side non-zero, but here I have right hand side 0. Can anyone tell me for which ij's will I necessarily get right hand side, and for which ij's I will not get right hand side to be 0? Can anyone tell me that? Looking at the pattern of the things, does it? It's kind of intuitive question. It's kind of you can figure it out by looking at the, when I equal to j. Well, not necessarily. That's not the peripheral point. Absolutely right. Absolutely. Those points which are in neighborhood of the boundary point, okay, their right hand side will not be 0. Okay, so all those points, not only corner points, even for example, if you do 1 2, okay, 1 2, you will get not 0 here. Okay, so you should try this. Okay, so basically all the idea is that if this is your boundary, okay, so if these are your boundary points, okay, so any point which is in neighborhood of the boundary points, the right hand side will be not 0. Okay, but if you're not in neighborhood of boundary points, okay, then your right hand side will be 0. So for example, 3 by 3 case, only 2 2, if you choose I equal to j equal to 2 and 2, okay, then only you will get 0. Otherwise all points are in the neighborhood of boundary points. Okay, so that's what is going to reflect in your equation, right? So maybe I can write down this that the RHS is 0 for those ij's here which reside in the neighborhood of 100. Okay, that is one thing. So that way you can actually guess or cross-check your results. Okay. There's one more important thing to note here is that the absolute corner points, meaning uh, meaning these points, this one, this one, this one, this one, are they important for us or not? Can you tell me, are they important for us? Actually, they are not important for us at all. They are not important for us at all. Okay. Yeah, I think I saw a couple of answers adjacent to boundaries. Absolutely right. Right. So that is where you get non-zero as this. Right. Yeah. Question is, the question is these points where the boundaries meet. Okay, the corner points. These are the 4 corner points where the boundaries meet. Okay. These points do not affect our solution. Why? Can you have any, can you think of looking at the method that we have, the scheme of the method that we have constructed, that automatically implies that they were counted, right? Counted meaning what? Meaning that, remember 5-point scheme, right? So if you look at these points, this point is affected by this value, this value, this value, this value, and this value. Okay. So these are the related. Yeah. Right. So no involve exactly. So right. So therefore, these sorry, we should have not seen this. So well, we what I'm saying is any interior point. Okay. For example, this one is affected by this one, this one, this one, and this one. Okay. So that way, this point does not play any role. Okay, this has no role to play. Similarly, this point will be affected by this one, this one, this one, this one. Okay, these are the 5 points which are interrelated. So this point does not affect any of the points. Similarly, this point does not affect any of the points. So these informations are not required actually as such. Okay, for computing the solution inside the bound, inside the region. Okay, so that is another thing we need to keep in mind. So the corner points do not affect the solutions. Okay. So the corner points do not solution inside. Okay. By corner I mean where the boundaries be. Okay. All right. Okay, so now, so having done this, actually, this all entire exercise is worth what? Why are we doing this? Well, of course, one thing is that you are able to get your unknowns represented in a vectorial format, but accordingly, your equations are actually going to change, right? So this form, what we had when you had represented unknowns in terms of matrices, right? U's, if you represent in terms of V's, then equations are going to look different, right? For example, here I had definitely right hand side 0, but here I have for certain cases they are 0, for certain they are not. Okay, is there a pattern in this? So answer is yes, you can check that. I'm going to give the pattern of the equation that looks like the following. Okay? So the G equation can be written in the following form. Okay, that would be essentially so we have this form A G And G, we all know what is G. G is something that we need to find out. So these are known. And G goes, so now tell me how many entries does G have? Number of entries in G, the vector G. How many entries does G have? N into n, absolutely. So n times n. Okay, that would be n times m entries in G. And therefore, the A, so therefore, A matrix will have what shape? I mean, what are the number of rows and columns? Just nm by nm. It's called the small n. That would be n by n matrix. Right? So that would be n by n matrix. Okay. So, for example, if you had a grid of what? Grid of 10 by 10 size. Okay, 10 this way and 10 in x direction points and 10 y direction points. Okay. Then you will be having 100 by 100 size matrix of A. Okay? So you can see that it's a huge matrix actually. All right. So just for small 10 by 10, you need to have 100 by 100. You have to deal with 100 by 100 matrices, right? 100 by 100 size matrix. Okay. And that A will be having a particular form that can be represented as a block matrix. I'm going to write this as a, just like a block matrix. Okay, so block matrix meaning what? Each element is actually a matrix itself. Okay, so I'm going to write down T, D, zeros each, D, G, D, zeros each, 0, D, T, D, zeros each, 0, 0, D, T, D. This is how it goes, right? These are all zeros. So this is the kind of form your, this will be n by n. Okay. What is T, D, and T? Okay. So T is a tridiagonal matrix. Okay. So T itself is a matrix. Okay. So this basically at each T you put a submatrix like this. There's a submatrix like this, and so on. These of course will have zero, would mean that all elements are zero. D is a diagonal matrix. Okay. So D has a particular form which is I think it's -1 each. Right? So we will be having a form which is we need to check this because I will have to check. I can recall. Probably we will be having C. So beta v1 v2 will be +1. So these, for example, so we would be -1, -1, -1. These are zeros each. Okay, and T would be, if you look at this, it has a similar form. That would be 1 minus lambda square, right? Minus lambda 1. So that would be having a form that is minus lambda square 0 each and so on. Okay, that would be a tridiagonal matrix itself. Okay, and they will be basically m by m, right? And they will be repeated n times on both directions. Okay, there will be n such rows. Okay, so they will be repeated n times this way and n times this way, so as to get mn by mn matrix overall. Okay, That would be your mn by. So these matrices will be. So there will be. Let's say 1, 2, 10 here. 1, 2, 10 here. That's how things look like. That's a kind of pattern I want you to be aware of. Okay. All right. So I want you to check these entries are correct or not. Okay. So you already know how to find those equations, right? In terms of V, getting too complex, of course. Well, yeah. But you are not supposed to be doing it. The computer does it. All you need to know is you understand the scheme, okay, and get the bigger picture, okay, and you just code it. Computer will automatically assign everything, okay. That's why this is worth it, okay. Uh, so yeah, it is well, I won't say it's too complex. It is complex, of course. So only reason that it's being complex is that you're trying to write your unknowns in a vectorial form. That's all. Okay. So this G is simple, but at the cost of writing A. Okay. Okay. So at the cost of writing A, now there is there's a catch here. What is the catch? You can see that there is a whole lot of entries in A which are zeros actually. It's a huge matrix. That's scary. Okay. So you can say that, for example, what I so the point to note here is that A matrix is huge. Okay. So even if by 10 gridding, okay, it goes to 100 by 100, that is 10,000 entries. Okay, in A. Okay, but most of them are zeros. But it is first of all, it is structured. There is a particular structure into it, right? As I showed to you, it's a tri-block diagonal matrix, okay? And each block diagonal itself has a particular structure. Each matrix has a particular structure like this. Don't worry, it's too much. Don't worry too much about remembering these. I just want you to understand that after doing this, what is the kind of pattern that emerges in the set of equations? That is what I want you to keep in mind. Okay. All right. So and see, rest is all you need to do is you have a simple rule given by this. Okay. So in the computing, what you do is suppose you have use. Okay. So for each well you can first of all, it's very easy to cut. What I'm saying is, if there is a structure in the resultant A matrix, it's very easy to code. Okay? You can make this matrix very easily. Okay, you can basically construct sub matrices and then join them. You know how to join matrices in MATLAB to make how to basically concatenate two matrices, right? So you can just join them. You can construct each. T is the same matrix. So once you constructed T, you're done. Once you constructed D, you're done. These are simple, and then you just join them. That's all. So just join in a particular manner so that these entries are zeros, these entries are zeros, and that's it. So that shouldn't take more than 2 lines. Okay. All you need to know is that there's this particular structure that would emerge out of all this exercise. But since there's a very simple structure, it's very easy to code. Yeah. All right. Good. So it's good that now you're not finding it too complex. Okay. All right. So once because all of them are in the same form, right? Okay. So first of all, it's huge, but it is structured. Okay. First of all, and secondly, it's sparse. Okay, that is a matter of concern. Okay, this is good for us because I can easily construct it. Okay, by simple logic, I can just give a one-line logic and the computer will construct it for me. Okay, because there is nothing great variation happening if we go from here to here or from here to here to here. They're all the same matrices, right? They're all the same matrices. They're all the same matrices. So I just and then join them in a particular logic so that I can construct this particular matrix, right? That's good, but it's a sparse. Sparse means what? A lot of entries are zeros here. If you count, so now I can ask you, I can assign you this homework, find out if there is n by n matrix, or let's say n or n and nm is are the two total number of points in along x and y. Okay, so if nm is equal to n, okay, then question is how many zeros are there in this matrix? Okay, that you can find out. Okay, please find it out. Okay, I can give you an answer. There are you can you should find this out. 5n minus 2 times n plus n. Okay. That is the answer. Okay. Remember, when you're counting zeros, remember each d has zeros and each t has zeros too. It's not just that you count these zeros and you're done. No. Each t will be having zero, each d will be having zeros. So just do the accounting, do careful accounting. I think you should arrive at this result. Okay. There are 5n minus 2 times m plus n entries. There are total entries n squared. Okay. Total entries are n squared. Okay. N is equal to mn. Okay. So say m is n, m is 10, n is 10. Example case, which is a 10 by 10, I mean, yeah, m by m, absolutely. So this is the m by m. So they have to be, if you're putting two blocks, they have to have the same size, right? So that's necessary. If you're putting two blocks contiguously, one next to this one, so these must match, and this should match with this. So number of columns should match D, because we're putting this D on top of T. Okay, so T and D should match in column size, and since we're putting D right of T, okay, therefore the rows should match with D. So since row and columns are matching with T, so D and T should have the same shape, which is m by n. Okay, is that all right, Mriga? Yeah, that's not very trivial to say that it's a very valid question, but you can check that they should be having m by m each, and they will repeat n times this way and n times this way. Okay. Okay. I have a simple logic that I'm giving. If you think T is m by m, then D has to be m by m because D is on top of T and D is on left of T or right of T. Okay, or left of T. So therefore, it has to have the same rows and same number of columns. Okay, and therefore it is m by m. Okay, so check this. So for a simple case of okay, so I think time. I'll just quickly look at this thing. N will be 100. Size of the matrix is 10,000, and total number of zeros entry, total zeros, would be equal to 5n. Okay, it's 5 into 100, 500 minus 2 times n plus n, that is 20. Okay, that is equal to how much it turns out to be 40. So result is correct. Oh, this is not total non-zero entry. That's what I was thinking. The total non-zero entries, not zeros, but it's opposite. So that's what I was. It's total non-zero. Yeah. Okay. All right. All right. I'm going to finish it soon. Okay. So that would be 440. Okay. So out of 10,000, only 440 are there which are not zero. Okay. So that is a problem because for most of the computing you are doing with zeros, which is very inefficient computing. Okay. All right. 460, right? Thank you. 460. So it's a very inefficient computing. So there are special methods devised. This is what is called sparse matrix. Sparse matrix where most of the entries are zero, very few are not zero. And in order to compute sparse matrix, I cannot just do Gauss-Jordan and those, because that will be too much effort for very little gain, right? Because most of them are zeros anyway. So that's where it becomes there are certain specialized methods dedicated for treating sparse matrices, right? So that's what will be useful for this case. Okay. All right. I'm going to stop here and we'll start the next class tomorrow. Okay. Okay. Bye bye.